In this problem, I am given the mass of a man, which is 75 kilograms, and the mass of a motorcycle, which is 125 kilograms. And I'm being asked to solve for the minimum coefficient of static friction when this man is trying to do a wheelie on the motorcycle. So what's the coefficient of friction that allows him to do this wheelie? And what's the acceleration of the center of mass of this system? So first thing I might recognize is, okay, I have a mass of a man, mass of a motorcycle, two center of masses, but these center of masses are for the man and the motorcycle respectively. What I really want to do is find a center of mass for my entire system. So there is an equation we can use. The equation is the center of mass in the x coordinate is equal to the sum of each of the position to the center of the mass of each of my particles times its mass, divided by the sum of the mass of my entire system. So this will give me an x coordinate of my entire system center of mass. So if you're not really sure what this equation means, it breaks up as follows. I want to take each of my particles, so I want to take the center of mass of my man and the center of mass of my motorcycle, and let's look at the man first. I'm going to have the distance to his center of mass, so this 0.4 meters right here, times his mass, which is 75 kilograms, plus the distance to the center of mass of my motorcycle, which is 0.8, times the mass of the motorcycle, which is 125, over the sum of the total mass, which is going to be this 75 kilograms for the man and 125 kilograms for the motorcycle. And if I simplify this out, I get a number that is 0.65 meters. So it's saying the center of mass of my system is somewhere over here, 0.6 meters from the point I'm dimensioning from. So let's look at try to get a y coordinate. So if I look at the y, it's equal to same thing as the x, but I'm just substituting y's in. And let's start again with the man. We have to go up 0.9 meters. And his mass is still 75. Plus, to get to the center of mass in the y direction of the motorcycle, I have to go up 0.6 meters. And the motorcycle's mass is still 125. So the denominator is still going to be this 75 plus 125. And if I put this into a calculator to get the answer, I get the center of mass in the y direction is 0.7125 meters. So what's this telling me? This is telling me that to get to the center of mass of my entire system, I want to go over 0.65 meters and go up 0.7125 meters. And that's going to give me a center of mass of my entire system somewhere around there. So, like I try to do in most of these problems, I want to draw a free body diagram in a kinematic diagram. If I can get this working here. Nope. All right, I'll just redraw my motorcycle. So and I'll draw the man on it. So this is going to be my free body diagram. And because I want to figure out the minimum coefficient of static friction to do a wheelie, this wheel is going to be off the ground, so there's going to be no forces on this wheel. The only force I'm going to have is a normal force on my back wheel and a frictional force. And my frictional force, if I'm moving in this direction, my wheel is going to be rotating clockwise. So my frictional force is going to point in this direction. And we just found the center of mass of my system. We know my center of mass of my system is going to have the weight of my system going through it. And it's going to be the total weight. So it's going to be this 75 plus 125 times gravity. And I'll just put up here, gravity is equal to 9.81 meters per second squared. Okay, so these are the three forces that are on this system. And now we have to draw the other side of the sum of the forces equation. So we're going to draw the mass times the acceleration side, our kinematic diagram. And when we do this, we're going to identify the center of mass. Center of mass is somewhere over here, and we're going to say it moves in this direction. So it has a acceleration of the center of mass is going to be equal to the mass, which is 200, times the acceleration of our center of mass. We'll just call it the acceleration of g. Okay, now from this free body diagram, we want to look at our three equations we use. We use the sum of the forces in the x is equal to the mass times the acceleration in the x direction. The sum of the forces in the y is equal to the mass times the acceleration in the y direction. And the sum of the moments about the center of mass is equal to 0. We want to use the sum of the moments about the center of mass is equal to 0 because this is purely a translational problem. We don't have any rotation on this problem. Typically, we have the sum of the moments about point G is equal to the moment of inertia times the angular acceleration, but this is just a translational problem, so there is no rotation, and it's just equal to 0. Okay, so let's sum our forces in our x direction first. And this is equal to the mass times the acceleration in the x direction. So we're going to have if we call it this way positive, we're going to have a frictional force is equal to our mass times the acceleration. I'll just make this g a little better. Okay, now let's sum our forces in the y. And our sum of the forces in the y is equal to the mass times the acceleration in the y, but there is no acceleration in the y direction. The acceleration is only in the x direction. So the sum of our forces for this problem is going to be equal to 0. So our sum of the forces, if we call upward positive, we're going to have this normal force of B minus the weight times gravity, so 200 times 9.81. is equal to 0. We can solve for this normal force at B, and we can get that this is equal to 1,962 newtons. Okay, one more equation. We just have the sum of the moments about the center of mass is equal to 0. And I'm just going to say this way is my positive direction. So about the center of mass, which is right here, my weight's not going to have a moment because it passes right through my center of mass. My frictional force is going to have a moment. My frictional force, if we're rotating this way, wants to go head first, and so it's going to be positive. So F times the perpendicular distance is going to be this distance right here, and it's going to be 0.7125, the distance we found right there. And this normal force at B, if we rotate it clockwise or counterclockwise around our center of mass, it's going to go tail first, so it's going to be a negative sign, and NB is 1,962. The perpendicular distance from here to here is going to be this 0.65. So this right here is 0.65. And this is equal to 0. Now, what can we do? We can solve. First we can either solve for the frictional force, or we can substitute. We know our frictional force is equal to this mu s times nb, the coefficient of friction times the normal force. So we're solving for what mu s is. Our nb is this 1,962. Minus this right here. And we can solve for mu s. And when we solve for mu s, the coefficient of friction, we get it is equal to 0.912. So this is telling us our coefficient of friction to be able to do a wheelie needs to be 0.912. So we have this part of our question, and we just need to figure out what our acceleration of our midpoint is. Well, we know what our coefficient of friction is. This frictional force is going to be this mu s times nb is equal to 200 times the acceleration of g. We just found what this is. This is 0.912. We know what this normal force at B is. It's 1,962. This is equal to 200 times the acceleration of g. And we can solve this for the acceleration of g. And if we do that, we get our acceleration of g is equal to 8.95 meters per second squared. And it's positive, so we know it's going towards the right.